Hello students, how are you doing today? Well, this is it. We're going to add dilations to our list of transformations today, making our transformation family complete. And then tomorrow we're going to start graphing with all of these transformations together. But before that, we need to become masters of dilations. In class, I gave you a worksheet today and gave you some advice to work on it a little bit before you watched this video. On these, they want us to graph this parent function, y equals absolute value x. So I'm going to quickly do that. I'm just going to kind of work through this very quickly. If you've already completed this worksheet and you're fairly confident that everything you've done is correct, you might want to fast forward. I think watching somebody fill out a worksheet that you've already filled out could probably be pretty boring. I think I'm just going to go through and put in all my absolute value x graphs right away, just because I got my straight edge with me. And this third one. In hindsight, perhaps I should have done these 4 graphs before starting the video. I feel like I'm wasting your time right now. My apologies, students. Okay, I'm going ahead and start putting in some numbers here. Let's see. 1x is -2, y is 2. Same thing, so 0, 0, 1, 1, 2, 2. Now, what happens if you multiply this y coordinate by 2? It becomes 4. 1 times 2 is 2, 0 times 2 is 0, 1 times 2 is 2, 2 times 2 is 4. And then bring out a different color for this dilation. So if I had the point -2, 4, I get that. -1, 2, I'd get that. 0, 0, 1, 2, and 2, 4. Connect the dots. And if you're doing multiple graphs, it's always nice to go multiple colors so that you can differentiate easily between the two graphs. Now, I noticed that they're calling this a vertical stretch by a factor of 2. I don't like using the word stretch and shrink. The number 2 in itself will let you know if this graph has been stretched or shrunk down. We're just going to use the word dilation. This is a vertical dilation by a factor of 2, and it appears to here that that equation is 2 times the absolute value of x. And it makes sense, because if you look at these y-coordinates, it was getting vertically moved up by 2. So it's outside of the function. So it's going to affect the y-coordinates. The y-coordinates were all getting multiplied by 2. Well, what's going to happen if the y-coordinates get multiplied by 1/2? Well, let's find out. The parent function would be exactly the same as the previous problem. And then if I did 1/2 y, let's see, 2 times 1/2 is 1. 1 times 1/2 is 0.5. Maybe I should have just said 1/2. 0, 0.5, and 1. I guess I prefer, when I do graphs, I think it's easier to think about it as decimals, I suppose. Anyway, let's see, we have the point 2, 1, 1, 0.5, 0, 0, -1, 0.5, and -2, 1. We connect the dots. And I think hopefully what you're noticing is that instead of these y-coordinates getting multiplied by 2, these y-coordinates got multiplied by 1/2. So this is a vertical dilation by a factor of 1/2. And if we follow our last problem as a previous problem as an example, if this one was f of x equals 2 absolute value x when it was 2y, the 1/2 would end up being 1/2 absolute value x. So kind of like before, the vertical stuff that's going to affect the y-coordinate, the equation ends up being stuff outside the equation, outside of the function. Okay, so that's vertical dilations, and then same idea. But what's happening if instead of going multiplying the y-coordinate by 2, what if you're multiplying the x-coordinate by 3? So the parent function would be the same, -2, 2, -1, 1, 0, 0, 1, 1, 2, 2. Then this time, instead of multiplying the y-coordinates by a number, we're multiplying the x-coordinates. That would make this -6. -1 times 3 is -3, 0, 3, and 6. And if I graph those points, -6, 2, -3, 1, 0, 0, 3, 1, 6, 2, connect the dots. Now in this previous problem, these these dots, the transformed dots lined up vertically, which is why we're multiplying the y-coordinate. Whereas on these, they're not going to, on these horizontals, they're not going to line up vertically, they're going to line up horizontally. And if you notice, this had an x-coordinate of 1, but now it has an x-coordinate of 3. This one had an x-coordinate of 2, now it has an x-coordinate of 6. So the x-coordinate is dilating, so that is a horizontal dilation. By a factor of 3. Now, think about this from the last couple days. On the inside of the function, we always do exactly what we're supposed to. So when we had a vertical dilation by a factor of 2, we're multiplying the inside by 2. But then for this one, when we do a horizontal dilation by a factor of 3, instead of being outside the function for vertical, it says horizontal, so it's going to be inside the function. And then instead of doing mathematically what we're supposed to, we do the opposite. So instead of multiplying by 3, we divide by 3. So when you divide by 3, that is a horizontal dilation by a factor of 3. Backwards and kind of confusing. What else did I want to say about that? I'm not sure. But anyway, so when you have this multiplying the x-coordinate by 3 in the equation, you're going to divide by 3. Oh yeah, you can always check if you're not unsure. If you plug the point 3 into this equation, 3 divided by 3 is 1, and you get your point 31. Or it's 6. 6 divided by 3 is 2. So you get the coordinate 6, 2. So a couple of those coordinates backs up our idea. Last one, parent function. I still have -2, 2, -1, 1, 0, 0, 1, 1, and 2, 2. But this time we're multiplying the x-coordinates by 1/2. So that would make this a -1, a -1/2, a 0, a +1/2, and a 1. And if we graphed all those points, I have -1. I feel like I've made a mistake here. I have -1, +2. Maybe I haven't made a mistake. -1/2, +1, 0, 0, 1/2, 1, 1, 2. Connect the dots. Connect the dots. La 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 la. Connect the dots. La 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 la. All right. There's our graph. And notice, vertically the points are not lining up. It's kind of hard to see, but horizontally they are lining up. So that is a horizontal dilation. In this case, by a factor. Now this time we're multiplying it by 3, so it's a factor of 3. This time we're multiplying the x-coordinate by 1/2, so it's by a factor of 1/2. which would mean in the equation it's f of x equals, now in this case we divided by this 3, so it's x divided by 1/2, but that looks really awkward, and x divided by 1/2, that's the same thing as 2. So 2x. So something to be careful of is that if you have this 2x, you might look at this and think horizontal dilation by a factor of 2. But no, this is a horizontal dilation by a factor of 1/2, meaning you're going to multiply the x coordinates by 1/2. All right, so to wrap a bow on just the theoretical end of this, a couple days ago we were, oh wait, I have a Desmos to show you. Let me move over, oh I got to into here, make Desmos bigger. I have a couple Desmos graphs to show you. There we go. Over here, okay, so I want to start off with this one here. So I had y equals x squared in one graph and y equals 3x squared. And as you can see, when you have an x squared and a 3x squared, the key points went from 1, 1 up to 1, 3, or it went from a 2, 4 up to 2, 12. So because we were multiplying the y coordinate by 3, or the function by 3, the y coordinates were getting multiplied by 3. Whereas one with a horizontal dilation, an x squared versus an x over 2 squared, and here, same thing. This key coordinate of 1, 1 became a key coordinate of 2, 1. So the x coordinates got multiplied by 2. Or the point 2, 4, you multiply that x coordinate by 2, and you get the point 4, 4. All right, so that's a Desmos look at this. Let's make this smaller. All right, make this bigger again. Okay, so just to finish this up. Sorry about this. All right. So our previous transformations definitions sheet looked like this. And this had the reflections in it, this positive, negative for the, with positive, negative in front. That's the x-axis reflection. The positive, negative on the inside for the y-axis reflection, traveling h units to the right and k units up, or just our horizontal and vertical translation. This is the new one. And this is the final one. And the only thing that I've added to this is I've added the letter B out front of the function. And here I added the letter A for the horizontal function. Perhaps you hear fourth period coming in. So if this B is out front, that is reminiscent of a, it's out front, so it's affecting the y coordinates. That's a vertical dilation by a factor of B. And if you have this divided by A on the inside, that would be your horizontal dilation by a factor of A. And that is the theoretical end of dilations. Part 2 of this video will be examples. And I'll actually do that in 2 parts. I'll run through some examples using team graph paper. Then I'll run through some examples using team graph paper. I'll talk to you later.